Introduction to Kepler's laws of planetary motion. In the early 1600s, Johannes Kepler unveiled 3 revolutionary laws of planetary motion. These laws described how planets move around the Sun, replacing older models that assume circular orbits. Kepler's work relied on detailed observations by Tycho Brahe and showed that planetary motion follows specific patterns, forming the foundation for modern astronomy and physics. This guide will explore each of Kepler's laws in detail. The law of ellipses. The law of equal areas. The law of harmonies. Kepler's first law. The law of ellipses. The statement: the orbit of every planet is an ellipse, with the Sun at one focus. Breaking it down, planets do not move in perfect circles. Instead, they follow an oval-shaped path called an ellipse. Imagine stretching a circle into a slightly elongated shape. This is what an ellipse looks like. The ellipse has 2 special points called foci, plural of focus. The Sun occupies one of these points, while the other remains empty. Understanding the shape. To visualize an ellipse, place 2 pins on a board. Tie a string around them. Use a pencil to pull the string taut and trace a shape. The traced shape is an ellipse. The farther apart the pins, the more stretched the ellipse becomes. Implications: planets like Earth are closer to the Sun at certain times and farther away at others. The closest point to the Sun is called the perihelion. The farthest point is called the aphelion. This law shattered the ancient belief that planets move in perfect circles and revealed the true nature of their orbits.
Kepler's second law. The law of equal areas. The statement: a line connecting a planet to the Sun sweeps out equal areas in equal amounts of time. Breaking it down, imagine a straight line connecting a planet and the Sun. As the planet moves, this line sweeps across space. According to Kepler's second law, the area covered by this line in a given time is always the same, regardless of where the planet is in its orbit. How it works: when the planet is closer to the Sun, it moves faster. When it is farther from the Sun, it moves more slowly. This change in speed ensures the swept area remains constant over equal time intervals. Real-world analogy. Think about a figure skater spinning. When they pull their arms in, they spin faster. When they stretch their arms out, they slow down. Planets behave similarly in their orbits around the Sun. Implications: planets move faster near perihelion, closer to the Sun, and slower near aphelion, farther from the Sun. This law explains why the length of seasons on Earth varies slightly. Kepler's third law. The law of harmonies. The statement: the time a planet takes to orbit the Sun is related to the size of its orbit. Breaking it down, planets closer to the Sun complete their orbits more quickly than planets farther away. For example, Mercury, the closest planet to the Sun, takes just 88 days to complete one orbit. Meanwhile, Neptune, the farthest planet, takes 165 years. Simplified explanation: imagine 2 race tracks, a smaller circular track and a larger oval track. A runner on the smaller track finishes laps faster than one on the larger track. Similarly, planets with smaller orbits move faster than those with larger orbits. Understanding the relationship. Kepler's third law reveals that there is a precise relationship between a planet's orbital period, how long it takes to orbit the Sun, and the size of its orbit. This relationship applies to all planets, moons, and even artificial satellites orbiting the Earth or other celestial bodies. Implications: Kepler's third law allows astronomers to predict how long it takes for any object to complete its orbit. It's also used to calculate the distances between planets and their stars in other solar systems. Why Kepler's laws are important. Revolutionized astronomy. Kepler's laws showed that celestial objects follow predictable patterns, moving away from myths and assumptions. Laid the foundation for Newton's work. Kepler's findings inspired Isaac Newton to develop his law of universal gravitation. Applications in space exploration. These laws are crucial for designing satellite orbits, space missions, and understanding distant exoplanets. Revealed the harmony of the cosmos. Kepler's work demonstrated that the universe operates according to beautiful and precise mathematical principles. Conclusion. Kepler's three laws transformed our understanding of planetary motion, bridging the gap between ancient beliefs and modern science. These laws not only describe the movements of planets in our solar system but also provide a universal framework for studying celestial mechanics. By understanding the elliptical paths of planets, the varying speeds at different distances from the Sun, and the relationship between orbital periods and distances, we gain deeper insights into the workings of the universe. Kepler's contributions remind us of the incredible power of observation, mathematics, and human curiosity in unraveling the mysteries of the cosmos.